When NASA's pioneering Voyager spacecraft ventured beyond the confines of our solar system, they encountered an extraordinary and enigmatic phenomenon that would reshape our understanding of cosmic boundaries. Scientists documented the presence of an intense, high-temperature barrier positioned at the outermost reaches of our celestial domain. This remarkable discovery, characterized as a blazing thermal boundary, emerged within the transitional zone called the Heliopause, the critical juncture where solar dominance yields to the vast expanse of interstellar territory. What constitutes this mysterious frontier? What revelations did Voyager's instruments reveal? Let us examine these findings in detail. The genesis of an epic voyage. The year 1977 marked a pivotal moment in space exploration. During this period, computational capabilities remained relatively primitive compared to contemporary standards, while aerospace technology was embarking upon its initial bold ventures beyond terrestrial boundaries. NASA orchestrated the deployment of two robotic explorers destined for an extraordinary odyssey, the twin Voyager spacecraft, designated as Voyager 1 and Voyager 2. These mechanical ambassadors initially received directives to investigate the massive gaseous worlds of our solar system's outer regions. However, their ultimate destiny extended far beyond these preliminary objectives. Their true calling involved penetrating the absolute periphery of our solar domain and advancing into the uncharted territories of interstellar emptiness. Following countless years of persistent navigation through space, sustained by compact radioisotope thermoelectric power sources and guided by terrestrial control signals that traversed the light-speed communication delay, these seasoned explorers achieved unprecedented scientific breakthroughs. The spacecraft encountered an astonishing and unforeseen obstruction, a colossal barrier, imperceptible to visual observation yet characterized by blazing characteristics and extraordinarily elevated thermal conditions. Deciphering the Heliopause phenomenon. The Heliopause boundary embodies a phenomenon considerably more intricate and active than a mere demarcation line plotted on celestial charts. This region constitutes the spectacular frontier where two formidable cosmic influences engage in collision. One participant in this cosmic encounter consists of the perpetual solar wind, a continuous discharge of electrically charged particles, predominantly protons and electrons, emanating from our sun omnidirectionally at velocities reaching hundreds of kilometers per second. This particle stream generates an enormous protective envelope encompassing our stellar neighborhood, termed the heliosphere. Envision an inflated sphere within a flowing river, but magnified to astronomical proportions. The solar wind expands this protective envelope, displacing the encompassing interstellar medium, the sparse gas, particulate matter, and cosmic radiation that occupies the void between stellar objects throughout our galaxy. The heliosphere's dimensions are truly remarkable. Its forward-facing region, the leading boundary aligned with the Sun's galactic trajectory, extends to approximately twice Pluto's orbital distance, while its trailing section extends considerably farther. The heliopause represents the crucial interface where the diminishing pressure of the weakening solar wind achieves equilibrium with the pressure exerted by the approaching interstellar medium. Rather than forming a rigid barrier, this constitutes a chaotic transitional region characterized by vigorous interactions between opposing forces. The thermal barrier revelation. Within this boundary zone, the Voyager missions accomplished their groundbreaking observation. Scientific instruments including plasma detection systems and cosmic ray monitoring equipment documented alterations in particle trajectories alongside a tremendous thermal escalation. Instrument readings surged to astounding levels, reaching approximately 50,000 degrees Celsius, equivalent to roughly 90,000 degrees Fahrenheit. Scientists metaphorically designated this phenomenon as the blazing barrier, or plasma boundary, potentially resembling a spherical structure. This observation naturally prompted fundamental questions. How can such extraordinary thermal conditions manifest within the vacuum of space? Furthermore, why didn't these mechanical explorers, constructed from metallic components and electronic systems, undergo immediate liquefaction comparable to frozen dessert exposed to microwave radiation? Understanding thermal dynamics in cosmic vacuum. The solution resides in comprehending the fundamental characteristics of thermal energy within space environments. Temperature in these conditions primarily represents a measurement of average kinetic energy, specifically, the velocity of particle motion, rather than thermal energy in the conventional sense associated with domestic heating systems or radiative warmth. The material density in these regions measures trillions of times below that found within Earth's surface-level atmosphere. Consequently, despite exceptionally elevated temperatures, indicating rapid individual particle velocities, the aggregate thermal energy these particles can impart to spacecraft structures during infrequent collisions remains minimal. This scenario resembles experiencing impact from sporadic water droplets traveling at tremendous velocities. While the collision would be detectable, it wouldn't result in fatal thermal injury. Voyager's engineering incorporated provisions for extreme space environments, including vacuum conditions and thermal fluctuations, while the sparse material density at the Heliopause provided protection against immediate structural failure. The fundamental physics of the thermal wall. This temperature elevation directly results from shock wave generation, more specifically identified as termination shock wave formation. When supersonic solar wind encounters interstellar medium, it experiences rapid deceleration, analogous to atmospheric compression occurring ahead of supersonic aircraft that generates shock wave phenomena. The kinetic energy contained within the solar wind undergoes conversion into thermal energy affecting particles, elevating their temperatures to tens of thousands of degrees. This complex interaction establishes regions of intensive turbulence populated by high-energy particles. Unexpected magnetic field phenomena. Voyager's scientific achievements extended beyond thermal discoveries. As these spacecraft traversed the Heliopause, they transported not merely particle detection instruments, but also highly sensitive magnetometric equipment. At this juncture, research teams encountered additional unexpected findings. Scientific expectations suggested that transitioning from heliospheric to interstellar environments would produce dramatic magnetic field orientation changes. A solar magnetic influence should surrender to local galactic magnetic field dominance. Nevertheless, data transmitted from Voyager 1, followed by Voyager 2, revealed contrasting observations. Analysis demonstrated that magnetic fields immediately beyond the Heliopause maintained orientations remarkably similar to magnetic field directions detected within the heliosphere. This represented an unforeseen magnetic alignment. Initially, data from a single probe, Voyager 1, left uncertainty regarding whether this constituted localized anomaly or widespread pattern. However, identical measurements obtained from Voyager 2, which crossed the Heliopause at an entirely different spatial location, separated by dozens of astronomical units southward, validated this remarkable phenomenon. The interstellar medium's magnetic field characteristics near the Heliopause demonstrated alignment with solar magnetic field properties. This revelation necessitated theoretical revisions concerning magnetic field architecture at our solar system's periphery and their interactive mechanisms, suggesting more sophisticated and potentially extensive organizational patterns within interstellar magnetic fields characterizing our local galactic region. Comprehensive scientific impact. The Voyager mission's importance transcends merely confirming Heliopause existence and quantifying its characteristics. These spacecraft delivered the exclusive direct measurements of conditions within this distant and challenging-to-access region. Each data fragment transmitted across distances requiring over 20 hours for radio signal propagation to Earth possesses immeasurable scientific value. This information has fundamentally transformed our comprehension of heliospheric structure and dynamics, our cosmic protective enclosure containing life within. The heliosphere functions critically as a defensive barrier, substantially deflecting galactic cosmic rays, ultra-high-energy particles that pose threats to both space technology and potentially biological systems. Comprehending how this protective mechanism interacts with interstellar medium, how it develops, and where its boundaries exist holds tremendous significance for astrophysical and heliophysical research, scientific heritage, and future prospects. The remarkable blazing wall phenomenon serves as evidence of powerful processes occurring at the interface between distinct cosmic environments. It demonstrates how solar energy undergoes transformation and dispersal at the extreme limits of solar influence. The surprising magnetic field alignment discoveries inaugurate new investigative directions for studying magnetic architecture within local interstellar space surrounding our solar system. Nearly 5 decades following their initial deployment, these compact terrestrial representatives continue operational status, transmitting unprecedented data from interstellar domains, territories that no other human-engineered objects have successfully penetrated. Advancing research, the IMAP initiative. The thermal wall discovery and magnetic field revelations at the Heliopause constitute not a concluding achievement, but rather a compelling catalyst for subsequent investigations, exemplified by NASA's IMAP, Interstellar Mapping and Acceleration Probe initiative, which will focus specifically on studying these boundary phenomena from reduced distances, expanding upon Voyager's foundational contributions. The IMAP initiative represents among NASA's most compelling and ambitious undertakings, scheduled for deployment within upcoming years. Although this spacecraft will maintain positioning considerably closer to Earth compared to the Voyager probes, its objectives directly correlate with understanding how our solar system engages with broader cosmic environments. This mission will monitor the heliosphere's boundary, the zone where solar wind confronts interstellar material. This location marks the authentic beginning of outer space. IMAP will function at Lagrange point L1, positioned approximately 1.5 million kilometers from Earth, situated directly along the Earth-Sun alignment. This strategic positioning enables continuous observation of solar wind and additional particle streams without disruption from Earth's magnetic field interference. Contrasting with the Voyagers, which followed linear trajectories away from the Sun, IMAP will execute observations from a stationary position, gathering information through sophisticated sensor arrays and spectrometric systems. The mission's primary objective involves creating comprehensive mapping of solar wind and interstellar medium interactions. To accomplish this goal, the spacecraft will monitor energetic charged particle flows, particularly energetic neutral atoms, ENAs. These atoms originate within the boundary zone separating solar and interstellar environments and contain information regarding heliosphere boundary formation and modification processes. Essentially, IMAP will function as a cosmic imaging system, generating three-dimensional models of the protective envelope surrounding our solar system. Real-world applications. Additionally, the mission will advance understanding of space-based particle acceleration mechanisms. This knowledge holds importance not only for fundamental scientific research, but also for ensuring practical safety during future human space missions, which hopefully will materialize. High-energy particles of cosmic origin present potentially lethal hazards for both space travelers and spacecraft systems. Despite its relatively proximate location, IMAP will operate within high radiation conditions and variable space weather patterns. Therefore, the spacecraft incorporates durable electronics, radiation protection systems, and adaptive thermal management technology. While it won't encounter extreme temperatures comparable to the 50,000 degrees Celsius found in the Sun's corona, it must nevertheless endure temperature variations between sun-facing heated surfaces and shadowed cold regions, similar to previous space probes. Final assessment. Consequently, IMAP represents the successor to the Voyagers, metaphorically their descendant. It will investigate our stellar system's boundary, collect previously inaccessible data, and provide humanity with mapping of that frontier beyond which authentic deep space commences. The mission integrates advanced technology, fundamental scientific research, and strategic importance for future exploration of the solar system's remote frontiers. Meanwhile, each signal received by deep space network antennas from the departing Voyagers provides humanity opportunities to observe distant and unexplored cosmic regions. These 1970s messengers, having traversed billions of kilometers, continue delivering knowledge that transforms our understanding of humanity's position within the universe at this very moment.